So again, hi everybody. I'm going today to introduce not specifically modeling tools, but if you work on InSAR, you should remember and take into account the three things I'm going to mention during this lecture. And I usually start this by saying that, you know, modeling is hard, much harder than you can believe. So the reality is that probably with Fabian or John, you're going to use numerical models that will be essentially an approximation of the nature by reducing to the simple elements, the things that we can consider. Like, for example, the crust, because it's formed of cold rocks, can be approximated as elastic material. And then in the case of volcanoes, we can simplify all the complexities of magma reservoirs into simple geometries, like a sphere, a prolate spheroid, or a dike intrusion that connected pipe to the surface. And essentially, the idea is that we have to make choices, and those choices are your experience. So far, we haven't come up with methods that make those choices automatically. So for the moment, we will have to work out with those assumptions about how the rocks will behave, how the stresses will be transferred, and how we will measure the formation on the surface. Essentially, when you determine which of the models and simplifications you want to apply, you will have to search in the model space in all the parameters and numerical values you can plug in that model, those that will explain your observations. And this part of the modeling step is called the inference or parameter estimation. So most of the work is essentially how to, for this given assumption that the user provides, the forward model, we come back to the model parameters number. And that's the well-known inverse problem. A solution can be obtained if we linearize the model. So there is here this capital G, which is an operator that relates those parameters, those numerical values you will put in the model, with the response on the surface, the displacement. The idea is that this G operator can be linear or nonlinear. If it's linearized, there is well-known least square solutions. More importantly, and that's where we will continue the rest of the talk, we should consider errors. And that operator should be weighted according to the uncertainties on the data. So what about this talk? This talk is essentially going to introduce how we can account for errors in the InSAR observation, make some remarks about the currently not clear a way to ingest phase and graphing errors, and few considerations about the geometry and the downsampling of the image. So in fact, it's three main ideas. We have to take into account errors in the inverse problem. We have to realize the geometric characteristics of the InSAR data is not information in 3D. And the fact that those numbers, the InSAR data is humongous, and we have to downsample it in clever ways. So if we have time, we may go to see one application in Volcano, but essentially probably we will skip that part. So the differential phase is complex, and I don't think it's a discovery to anyone, but even in our best efforts, PS analysis, we try to reduce as much as we can the correlation noise, stacking to reduce the temporal correlated atmospheric noises. There will be, in many cases, interference that will be dominated by noise. And what type of noises? We will essentially comment about two main sources, the most important ones. It's not that there are not others, but the most important ones are the ones that coming from the decorrelation, essentially the easy way to see about this decorrelation is the temporal changes of elements within a pixel that reduce the phase stability, increase its variance, and it looks much noisier, our interference. And those that even the coherence is really good, we will not be interested. In the case of deformation, these InSAR atmospheric noises that you have heard yesterday, somehow we have to account. So we have for our noise characterization to take into account the correlation and atmospheric signal. And why I make those separations as well is because essentially the way that we can characterize the noise in the data is through the stochastic modeling, something called the variance covariance matrix, and you will understand soon why this is important. So if most of the scientists are used to think about a sigma. So let's make a measurement and repeat it many, many times. And we think our instrument has a certain intrinsic noise that is propagated to the observation. So somehow we have to think that we have an instrument that instead of measurement through time, it measures through a space. So each single pixel is our thermometer, for example. And each pixel will have this associated sigma. If we unfold the whole interferogram, all the pixels in one vector, we will have the data variance vector. So each pixel has its associated sigma. Okay? That's the most usual way that people think about errors. However, the second source I was mentioning, the atmospheric signals, make InSAR extremely and less intuitive than many other observations. The fact that our data is not only characterized by a noise of that particular pixel, but a noise that is propagated and is correlated in a space. How that is represented mathematically is with this variance covariance matrix populated, generating coefficients along the off diagonal. So the data vector represents the main diagonal of that matrix, where we have number of data points in the interferogram versus number of data points. If you compare the correlation between one pixel with itself, is the variance, and that's why it goes along the diagonal, so the same coordinates in one of the two axes. And the coefficients that will go outside the main diagonal accounts for the correlation. So each measurement is not independent, it's very clear. That's the main idea you should take of this lecture, is that errors are of two types. One, spatially uncorrelated, we can approximate with the correlation and coherence. And second, atmospheric signals. And we will see this, how to populate this data covariance matrix. So how to populate it? Let's start with a simple way. We have a thermometer and we want to analyze how the standard deviation, the variance of the data is for each pixel. Our best guess to that type of noise is to calculate its local statistical properties. We will look at the consistency in the phase and amplitude in a small region around each pixel. And we will probably have heard during this week about the coherence, right? The coherence is the magnitude of the correlation between the phases at a very small scale. And it will be a parameter between 0 and 1, indicating 0 correlation, so completely random samples, or very homogeneous, same value samples when coherence is 1. So that underlies and try to estimate a process called the correlation. And the correlation has physical reasons why it occurs. And I will not enter in much detail, but essentially from all these terms, the easier to understand for everyone is the temporal decorrelation. So we have elements within a given pixel, and those can change in time. If we illuminate one pixel, the amplitude and the phase of that particular pixel is not a single value. It's the summation and the integral of many different elements. And if the elements change in size, in position, and dielectric constant or reflectivity, we will have a different sum of that. And that will induce changes. Very intuitively, if we make an interferogram spanning only one single day of temporal separation, the phase looks very continuous, although with its variations related to atmosphere. If we combine two stings separated by 1 year, we start to see this confetti type of texture. That is essentially coming from the changes in properties inside each particular pixel, losing the spatial correlation of the signal. Instead, to a point that the longer you make interferograms, the less useful pixels you will have, because many of them will have endured changes inside its pixel structure. So how we quantify this for something that we can measure, as it is a statistical stability, is coherence value, how we translate that to a sigma, a standard deviation associated to that particular pixel. So there are well-known models that relates the correlation to the result of motions within each particular pixel. So if we think on a large number of scatters, elements inside each pixel, and they have its own random motion characterized by its movement in the across coordinate and along path coordinate. If we assume this type of behavior, which is kind of a Gaussian behavior, we can relate the motion of the pixels to the uncertainty in the measurement of the phase. You just need to realize that because it decays, so the larger is the motion of those pixels, the larger will be the uncertainty. So we have, as we said, a way to express now the coherence as a phase standard deviation. So we measure the coherence, we estimate the coherence, and then using this approximated equation, or more sophisticated ones, if we have taken into account the number of looks in the sampling, we can convert this into a phase standard deviation. That's the way that we can populate the main diagonal. It's not the only way, but this is the main source of uncertainty that comes into the main diagonal of the data covariance map. What about the off-diagonal elements? Essentially, what we want to do is to have a sense of how strong in magnitude and how is the texture of turbulence in the atmosphere when we try to characterize the noise. So noise has been characterized in interferometry since the works of Ramon Hansen in the late 1990s, where changes in phase delay were related to turbulence in the lower troposphere. We can see much more less structured or more structured signals like gravitational waves. When you will see many interferons, you will see that the wind passes over mountains, and those will produce changes in pressure and temperature, and that will be seen as these very funky patterns in interferons. So how we characterize that type of noise? As I say, when it's uncorrelated, we have the trick of the coherence. We can move that or translate that coherence into phase standard deviation, and we have the main diagonal. Now, how we characterize the way that noise is correlated in space? So we have to move into geostatistics, usually, or signal processing. So there are several different tools that we can use. For example, the autocorrelation function is if we compare the signal with its own signal, and we start to shift it to see what is happening to it. So we will have maximum correlation when we compare the signal with itself. When we move it slightly, we will have lower and lower coherence. So that's what is the autocorrelation function. Very popular when we analyze in the Fourier domain is the spectral index. We can take as a time series or symmetrically averaged samples of an interferogram and look at the slope in the spectral domain. So where this axis represents the wave number, so how is related length in this transform domain and the power of the signal at each different distance. Usually we will see that the atmosphere is characterized with two different slopes, one related with a very strong troposphere between 500 and 2 kilometers, and a slightly less inclined, less power on longer distances. However, it's much more easy for novice, for beginners, to think on the covariance function, and I'm going to dedicate the next few slides on the covariance function. The covariance function is very simple to calculate because it's just simply the product of the phase of one pixel with the phase of a pixel at a certain distance. That is the covariance. We want to, the first thing is to take an interferogram, and this is the coherence map of this interferogram, and this is the phase change. So to calculate and to use this covariance function, we will start by computing the empirical covariance function, which requires to take a random sample of pixels across the coherent pixels of this interferogram. And for each possible pair, and you can see this can grow very fast, very quickly. For each pair, we multiply the phase values. And then being according to the distance, so the distance between this pixel and this pixel is going to be very similar to this and this, so we can average them according to the distance, and to obtain this gray line, which is how the signal is related to each other as a function of distance. So higher values represents very high similarity, and lower values is very different. The idea is that the slope and the way that it's decaying inform us of how overall on the interferogram the signals are related to each other. So one pixel is related to each other. So far we have obtain an empirical sample of how the signals decay with distance. And that is a simple way to characterize the atmospheric noise. However, with that, we cannot yet calculate the value of the covariance at each pixel in the interferogram. We only have a sample. So we have to have a model that we can substitute this R distance for any given pair to predict and to simulate what will be the level of correlation between two pixels. And for this, we will use theoretical covariance functions. And there are many, many different ways to simulate this decay. We can think on an exponential decay, a Gaussian decay, or special mathematical functions like Bessel functions joining other exponents. So as you can see, those mathematical expressions will be highly nonlinear. And if we want to fit to the observed data those models, we will have to solve a nonlinear optimization problem. In the slides, and you will have access later, I just give you for an example of how we can do that in MATLAB by using the simplex algorithm. Simplex algorithm is a free derivative nonlinear optimization algorithm for which we will minimize the difference between the theoretical model and the observed empirical covariance, so that we end up with a set of parameters, the optimal parameters for, in this case, A, C, and B. And now that we have A, B, and C, and this theoretical model, we can simulate any any correlation at any given distance. So now we can go back to the full interferogram and say, okay, I know that the distance between those pixels is 10. Plug 10 in this equation, and because I know A, B, and C, I can know its level of correlation. And now we can populate the off-diagonal elements of the variance-covariance matrix. I should here make a remark, because in the last session, I suppose we will use GBs, right? And you will hear not about the covariance function, but the semi-variogram. And it's just flipping the coin. It's the same thing in the sense that covariance trying to account for the correlation distance, how it decays the correlation with distance, where the semi-variogram tend to estimate at to what level the variance of the data will flat. And it's complementary. So if you estimate parameters for the semi-variogram, it will have a similar logic. You will have to take samples, assume that there is homogeneity in that sample, estimate whatever expression will characterize the semi-variogram, and with those coefficients, you can simulate the noise everywhere. So how does it look if we take a random sample of 1,000 pixels in a given region, and we estimate is according to these A, B, C parameters, we can find situations of which the correlation between points is very, very poor. It's almost every single pixel, it behaves independently. So in fact, the variance-covariance matrix will be dominated by the diagonal element and almost zero everywhere else. How does it look in the interferogram itself? It looks like a salt and pepper, confetti type of noise. So out of the noise that is dominated by pure decorrelation, we will have very poor correlation, spatial correlation. And that's what it looks. And this is just simply one realization of possible noise. And how the noise can be realized or create multiple samples of noise that has the same characteristics as the observed interferogram is to multiply this variance-covariance matrix by a random sample, so a random matrix. And you can generate many, many random matrices multiplied by the same variance-covariance matrix, and you will generate multiple times noise that behaves the same as you have observed, but is slightly different. And that's a very untraditional way to account for the fact that atmospheric noise will be present in any interferogram that you will to interpret with models. When the correlation in the data is much stronger, we will have much more populated variance-covariance matrix. And that results in much more structured, you see features in the simulated noise. In fact, because this comes from unobserved interferogram, it should be at least similar in texture as the observed interferogram from which you have estimated the variance-covariance matrix. So variance-covariance matrix in this context, I'm only talking about one interferogram. If we think about multiple interferons, we have to think of each variance-covariance matrix for each interferon in a humongous matrix. On each diagonal element will be one block representing one interferon. That tends to be computational intensive and probably not fitting in any memory, the computers that you will have available. So many times we neglect this spatial correlation. But it's our duty to tell you that the noise is there. The perfect way to interpret the models, it will be to account and introduce these correlations. So just recapping, we are halfway through, but I think this is the most important part of the lecture, is that data, the noise in the data has to be characterized. And if you want to neglect any other things, the ones that you can easily introduce in your data workflow is noise related to uncorrelated processes, like temporal decorrelation, that we can really obtain. Any single software interferometric package is able to calculate coherence. So you have this parameter, and it's just trivial to calculate this expression. So you will have at least some relative sense of which pixels are more reliable than others. And that allows you to populate the diagonal of the variance-covariance matrix. And if you are a little bit more handy in math, or you use GBs, for example, we will have to account for a spatially correlated noise, like the main source is the atmospheric turbulence, from which we will have to realize a small sample, fit a model, generate the variance-covariance matrix, and then validate and generate these off-diagonal elements in the data covariance matrix. So what about the rest of the lecture? So just mention that phase and graphing will be prevailing, and it's almost unavoidable. You probably have heard what it is. It's just simply removing the two-dimensional ambiguity in the phase that is carried by the differential phase and reconstruct the absolute phase. But just to mention what it means in terms of modeling is that it's a nil conditioning integration problem. In the case that we don't have noise in our interferons, there is always a solution, and it's easy to obtain. But our interferons contain a small and perceptible noise that trick numerical algorithms. So in fact, even in highly coherent interferons, you will obtain phase and graphing errors that you cannot be sure they are not there. So it's not explicitly accounted. And the traditional way is to assume they are small or they are not affecting the area of interest. Or in the case that's affecting the area of interest, you will make a huge effort to correct them manually. So what about the geometric considerations of the radar? Probably you have already been seeing the fact that pixels are not sampled in geographical coordinates. They are sampled in radar coordinates. And it takes a little bit of time to realize what that even means when you see interferons like this, so that in fact you are sampling along this line and not this other line over here. So considering that areas of your interferon will not be viewing the regions that you are interested in. Many cases when you study faults that are associated with very steep topography, which means that you will have not sampled complete regions of the horizontal coordinates where the formation is occurring, but we don't observe it. So phase jumps may occur over this overlay or shadow areas. What about the different line of sights? Traditionally, we have only have to cope with the strip map viewing. The strip map means that as the satellite moves, the energy of the pulse of the radar is sent in the Doppler direction. It's perpendicular to the advance of the satellite. And that makes exactly, in case that you have a phase delay in your interferogram, is along that line, that perpendicular line. But technology advanced, and spotlight and other like TOPS viewing and acquisition geometries were developed. The spotlight, you have to, depending on how is your level of the detail that you want, using the same approach as the strip map is incorrect, because the way that the line of sight and the energy was sent to the terrain is with a variable squint angle. So if in the case of a strip map, the squint angle, this angle between, as if the satellite move is looking backwards or forwards, in this case of the strip map, is perpendicular. In the case of the spotlight, some pixels will be illuminated with different variable angles. That's the way that is obtained at high resolution. And it has a small effect in the viewing geometry of each particular pixel. More relevant to most of the users is to account for the fact that TOPS, the Sentinel-1 acquisition mode, has this sweeping mode, but in reverse sense as the spotlight. So it's a start pointing backwards, and as it moves, change electronically to point forward. It's not a huge effect, but it's there. We have been talking about this sweeping angle, the squint angle. Either it's perfectly perpendicular or it's variable across the interferogram. And we have to also mention the look angle and the incidence angle. I always get confused. So the look angle is usually annotated in most of the files associated to your interferogram. Is the angle that is the satellite is pointing to the ground. From the vertical of where is the satellite to the center of the steam, usually. If you pay attention, we are not on, we cannot apply planar geometry on when we think about Earth. So if we were in a perfect triangle and we were in a planar and Cartesian space, this angle, look angle, will be equivalent to the incidence angle. The fact is that Earth is spherical, and when you move such long distance, so this is about 800 kilometers, that means that this angle will be slightly different because the reference surface has been changing. So incidence angle is the angle that matters when modeling. Forget about look angle. That's just, it's going to be a close number, but it's not the number that you have to use. The one that you have to use is the incidence angle, is how the ground moves at local scale, at the point that you have illuminated. The heading angle will also be important because the satellite will have side-looking geometry as any radar, and as you will move closer to the poles, this side-looking angle will change from the traditional east-west sensitivity to have more north-south sensitivity. So you probably have heard InSAR can only measure vertical, slightly east-west, and nothing in north-south. But that tells you it's not true. It depends on where you are on Earth. Combining ascending and descending angles and different side-looking interferograms, in fact, we can characterize better how the ground moves due to geological processes. That's just representing usual simulation of a volcano on which we can obtain the predicted displacement in the east component, this north-south component, and vertical component. If we apply the usual coefficients at mid-latitudes, we have the fact that east-west from what is real to what we can sense has dramatically reduced. So we have less sensitivity for east-west. As you can see, almost imperceptible in the north-south component. And as rain change, the polarity of the vertical motion will change, but it's essentially almost complete. The interference is the combination of all these components. If the displacements are sufficiently large, there is other techniques that just simply differential interferometry, which is, for example, the multiple aperture interferometry of MIA, that is able to sense the motion along the direction of the track. How? Is by combining or generating two synthetic spins from artificially modifying the squint angle. So let's synthesize an image that is slightly looking forward and one that is slightly looking backward. And by doing the difference between those two images, we can obtain a phase that is not sensing the change in range, but the change along the azimuth direction. This tends to be much more noisy and less demanding in coherence, so it's less practical. But if you are working on a very arid desertic area and the coherence is high and the displacement are in the order of a meter or more, you could eventually succeed to measure. Just saying the same thing, just emphasizing the fact that tops is the combination of those bursts. Each burst illuminates the ground slightly differently with different angles on the screen, and that will have to be taken into account. As you can see, pixels on the image could be illuminated several times with a slightly different incidence and looking angles and squint angles. So that could be a source of problems, or if you embrace the complexity, it could be a source of more information, more redundant information. But that requires that each particular burst will be processed independently so that we have a good sense of what is the geometry inside each particular pixel. So, and we actually, a few years ago, we tested the fact of how important was these slight changes in geometry for modeling of volcanic eruptions. So this is an example of a photovolcano in the Cape Verde Islands, where Sentinel-1 illuminated the terrain. In the case of the descending pass, the two bursts that illuminate the island were in fact coinciding with the intersection between or the area that was affected by volcanic intrusion. So we calculated carefully the squint angle, this deviation from the heading for each pixel, for each individual burst. Instead of having a mosaic, we processed it to have an interference for each burst, and we accounted for those variations. The reality is, even in that case, where we have significant deformation in the burst overlap region, in this case, it was not relevant. But in fact, you can be very accurate in the fact that you model the displacement on any given point if you know the incidence angle, the heading angle, and the squint angle. And how does it translate is that those angles can be factoring the east-west, north-south, and up and down components of your simulated model to obtain the observed line of sight. Pay attention that by doing this, you could essentially reproduce as well the phase jumps that you will be observing due to differential motion between the, just say, different viewing angles at the intersection between first. Just a reminder that we usually talk about radar coordinates, and that do not reflect directly to, we have to geocode those radar coordinates. And to be ready for modeling, we have to have the unwrapped phase and a matrix for each pixel related the three angles I mentioned. So the most important ones, the incidence angle and the heading angle. But you can also generate a squint angle maps for the modeling. So I mentioned, again, the last few minutes, I will mention the fact that the interferograms, if you think about it, they are composed of millions or tens of millions of pixels. And if we think on the computational cost of simulating models for which we need to have tens or hundreds of thousands of possible parametrizations, the fact that we model every single pixel in an interferogram is very time-consuming. So the fact is that most modern computers can handle it easily, about hundreds to thousands of pixels. Why? Because then for the needed data covariance matrix, we have to multiply this 1,000 times 1,000 to generate millions by millions matrix, that variance covariance matrix. So there are several methods that exploit the spatial correlation because the deformation is not independent. So when a volcano inflates, the deformation experienced by one region of the volcano is not completely independent of what you can observe 100 or 200 meters away. The idea is to exploit the spatial correlation to retain the most information possible from the deformation point of view. And there are several methods like the data resolution matrix method of Lohmann, the curvature of the deformation field, the famous quadrille method, and a uniform simple approach. So depending on what type of modeling or source model you are applying, sometimes it's not necessary to do a fine detail scale representation of the deformation field, but in the case of earthquakes, it tends to be very useful because earthquakes, when they rupture the surface, will produce discontinuities in the displacement field. And when you use homogeneous uniform sampling, that tends to produce a very coarse representation of the field, or could lead, if you want to preserve the details, to very inefficient way to downsample the interferogram. There are other ways to subsample the interferogram. In the case of volcanoes, it makes sense to sometimes have circular radial sampling of the deformation if you expect the deformation to be centered at the summit of a volcano. So other ways is shameful promotion of my approach is to use the triangular irregular networks. If you have something that is extremely irregular and not starting from a grid of points, that usually is the consequence when you do PS analysis, you will have irregular, topologically irregular list of points. We could essentially either approach quadtree or using triangular irregular networks. By looking at the residuals that you can generate to approximate the original observed deformation field, you can be more accurate when you are dealing with very irregular discontinuities like coastlines or surface ruptures due to earthquakes. In the case of irregular triangular networks, you can dramatically reduce the number of points to characterize the fault zone in the case that the fault do not align to the grid of your geographical coordinates. And when we look at the behavior in the data reduction tolerance of the two algorithms, you can see that it's smoother in the way that it describes the displacement field. And this is the practical application on which I apply this method. It's starting from PS analysis of a certain region where it's illuminating an island and it has a very irregular coastline. We could simplify the data point, preserving the areas that they are intense deformation and representing the irregular coastline. So in the last slide, I was just saying that again, that you will have to make the decision of which model you will to use. And then you will essentially find objective ways to decide which parameters explain better your observed deformation. And those are two very simple analytical expressions that you will see probably and apply later today. In volcano deformation, we use MOGI sources, spherical pressure sources, or dikes that the same formulation applied to faulting, the famous occurrence. So to conclude, three things, very important take-home messages. First, we have to for modeling, we have to characterize the noise. Please don't only use the main diagonal. It's easy, but it's not complete. You are not honoring the noise in the data. For that, we will use coherence, for example, to characterize the main diagonal, and geostatistical methods to analyze the correlation between data to populate the off-diagonal elements of the variance covariance matrix. InSAR do not observe the complete three-dimensional displacement field, so we should be carefully considering the three angles that characterize each particular pixel. So for each pixel in an interferogram, calculate incidence angle at the local scale, heading angle, and the squint angle in the case that you are working with Sentinel-1. And finally, we have to downsample the interference. And in that case, use popular methods like quadtree could substantially reduce the time for calculating and obtaining successful model parameters. So with that, I finish, and I will be happy to take any questions. Thank you.
In the simulation, you mentioned that you have to fit the variance covariance by some model, and after that you have theoretical covariance. Can you say me more detail? In case I have a variance and covariance model, how can I simulate the noise?
In the case that you can you?
Yeah, I have a variance and covariance matrix. Mm-hmm. So how can I compute the noise from that matrix?
exactly when you have this variant covariance
Yeah,
matrix,
I already have.
you
How
already
can I
have,
make the next one?
you have to generate another matrix of the same size, and
Yeah.
for each pixel, realize one random number between 0 and 1, for example. For each pixel, you will have, so like, for example, if you are in MATLAB, you will use the round function and then says the size of the matrix you want to generate. And that's just simply a multiplication between those two.
Yeah, so I didn't fix like you use the realizer. I have used another model is available, and from the model it has parameters so that I can compute the covariance and variant covariance matrix. Yes, for that one.
Yeah.
And I just want to make the simulated noise from that matrix. Yeah. So how can I?
So you will have this data will be equal to the multiplication of this matrix times another matrix, and that other matrix is just simply noise, pure Gaussian noise.
So it means that I can make a random noise.
Exactly. And every single time that you realize a noise, you can multiply, and you will generate a slightly different noise with the characteristics of the interference.
Okay, yeah. And another problem, it is correct that I faced with the problem with the memory of the matrix. As you know that just only 1,000 pixels. We are faced with a million of
billion
so
by billion.
I just want to avoid the downsampling and after that upsampling. It's a way we can do it. I just want to use smaller windows with overlap, and I simulate for. So have you got any advice for that?
So this looks very dense, but in fact, most of the when you look at the whole interferogram, it will decay much faster, as the example before. And the appropriate block will be that one that contains all the correlation distance. So if the correlated noise is decayed at 5 kilometers, you can make windowses of 5 kilometers.
Yeah,
overlay. And to generate a sparse matrix based on a recurrent or iterative method that goes and look carefully on each region of the interferogram.
Okay, thanks.
But it's, sometimes there is a lot of redundancy. It doesn't need
Thanks for the great talk. Since you are here, I would like to ask you a question. I'm not familiar with InSAR, but I'm coming from a GPS community. We are very fussy about uncertainties. So in InSAR, it's hardly in publication that you see when you have a rate map. You have another map of uncertainties. Yeah. Do you have an explanation why?
So in fact, those figures come from a method I developed in 2011 to start to associate an uncertainty, which is complete in the sense that we took into account turbulence and coherence as a guidance to generate the uncertainty in the rate maps. But more and more, we are seeing uncertainties maps associated to rate maps. Yesterday, for example, David Becker, that was here a few years ago as a PhD student with Tim Wright, just published a paper in Remote Sensing of Environment, on which he estimates displacement maps and rate maps in the Sacramento Delta in California, and associated actually an uncertainty map to his rate maps. How good is that uncertainty relates to how linear is the motion as well. It's complicated to represent uncertainty, but definitively give a go and try to produce uncertainty maps as well. If you haven't done it, follow me on Twitter. Not Twitter. Okay, maybe next time. Thank you.
All right, so again, coffee now, and then I think we're going to come back in here. I just have to track down John, see what he wants to do. chance we may go start some modeling, but most likely we'll be back here afterwards. I would not, well, we'll leave this out there, so yeah, I guess it's okay to leave stuff.
Let me turn off the video.
Okay, let's save it.
I want to save it on my
Yep.
my web pages. Where did
I